This is a quick video to show how exponential functions and logarithmic functions work together. So a logarithmic function is any function that is of the form of y, or f of x, is equal to a base value to a power of x. The base is generally greater than 0 and not equal to 1, and if the base is a fractional amount, you get a decreasing function, and if the base is larger than 1, you get an increasing function. The below graph shows three graphs here that are all three are increasing functions. If you notice, they all go through 0 and 1. Any value of a base to 0 is going to always equal to 1, so all three functions go through here. As well, you can kind of see here at 1, you can see the values, because base to the value of 1 is always going to be the base. So this first one here in red, it's going to have a base value of 2. So this is actually y equals 2 to the x. Here, my base value is going to be y is equal to 3 to the x, and here y equals 4 to the x. If you had fractional amounts, then we would have, say, a base of a half. It would also go through 1, and then it would be as a decreasing function this way. They also never cross over the x-axis. They're always positive y values. As a result, we have the following features of exponential functions. Whenever you have an exponent value of 0, because b to the 0 is equal to 1, we will always have the coordinate point 0, 1. Now these are also generalizations when there are no transformations applied. Whenever x is equal to 1, then we'll always have b to the power of 1, which is going to be just b, so we always have the coordinate point 1 and the base. We have a horizontal asymptote at x equals to 0, or sorry, y equals to 0. I should change that. There you go, y equals to 0. And then we also have our domain, which is going to be all real values, and our y values have to be strictly greater than 0 because they don't touch that asymptote at 0. Now the set notations, we have our domain and our range, and then this is interval notation here. Round brackets, because it technically doesn't equal a conceptual value of negative infinity and infinity, and same here, it does not reach 0. These are two graphs of exponential functions where we have our 2 points that we know about, one with a fractional base that's greater than 0, and then a base that's greater than 1. Now a logarithm is basically just an inverse of an exponential function. On the left-hand side, I have an exponential function with a base of b. We can write it as f of x equals b to the x, which then has those 2 key points that we just talked about. The domain and the range are here. Now here we have our log base b of x, or our f inverse of x is log base b of x. And we're going to take a look at how they're related in just a second. We can basically switch between this format and this format just by switching back and forth. If you notice here, it also is a reflection over the line y equals to x. It's a direct reflection. And our domain and our ranges switch. So how do you evaluate logarithms then? Well, every logarithm can be rewritten as an exponential. Basically, a logarithm is the exponent. So when we have a statement log base 5 of 125 equals to something, let's call it x for right now, that is equivalent to saying 5 to the x is equal to 125. So we can then see, well, what value of x is going to give me 125. We also know 5 cubed is going to equal to 125, so therefore x is equal to 3. So the same idea here, 2 to the what exponent will equal this. 2 to the x is going to equal root 32. So how can we figure that out? We do know that 32 is 2 to the 5, but we are inside of a radical here as well. So 2 to the x is going to equal the square root of 2 to the 5th. We need to have an exponent format, so 2 to the x is now equal 2 to the 5 over 2 because the square root is the same thing as a half. So now we know that x is going to equal 5 over 2. Now the same thing here. Now we know what our exponent value is. We don't know what the log is that we're looking for. So we can write it as 64 to the 2/3 is going to equal to x. We want to ultimately find the cube root of 64 and then square it to figure out what x is. So we know that the cube root of 64 is going to be 4, so then we have 4 squared is equal to x, so then we have 16 is equal to x. So we can rewrite this as log base 64 of 16 is going to equal 2/3. Same idea here. 5 to the negative 2 is equal to x. When we have a negative exponent, it's the same as 1 over 5 squared, which would be 1 over 25 is equal to x.